Hello everyone. Welcome to the presentation of Accelerating the IP Design Cycle with Formal Techniques Beyond Everyday FPV topic. As the name suggests, in this presentation, I'm going to talk about formal techniques other than FPV that can optimize and shorten the IP development lifecycle. Before I get started, I would like to thank my colleagues and co-authors Shaman, Narayana, and David Cassetti for their guidance and contribution in the paper and the presentation. I will start the presentation with acronyms and their description for some of the terms that I'll be using. Then I will move on to the introduction section, which will put some light on the motivation behind this topic. From there, I will talk about three formal techniques: formal elaboration, design exploration, and formal sequential equivalence along with their applications. In this, first I will discuss about the technique and then its application along with the problem that it solves. In the end, I will go over results that shows clear impact of these powerful techniques and will wrap up with the conclusion. Here are some terms such as silicon, formal verification, proof of concept, pre-silicon verification, which is also known as dynamic simulation-based or constraint-based random verification, logic equivalence check, and formal property verification, for which I will be using respective acronyms throughout the presentation. With this, let's get into the introduction section and understand the motivation. In this highly competitive era, IP development teams are required to deliver tape-out quality designs to challenging schedules. Out of all the activities involved in the IP development lifecycle, PSV activities are a major portion, approximately 50 to 70% of the total IP development time. Due to this, PSV has become a major challenge and the critical path to tape-out. Hence, IP development teams are constantly looking for ideas to efficiently reduce the time required for the verification. Now, as most of you might know, FPV is a well-known FPV-based technique to accelerate verification activities. This is mainly because, unlike PSV, it does not require any complex test benches. And in addition, it is exhaustive and can catch corner case bugs faster than the constraint-based random verification. Now, we had similar challenges in the design of our hardware compression IP. Some background information for the folks who are not familiar with hardware compression IP. In the simplest form of working, a hardware compression IP consumes uncompressed data as input and produces compressed data as output. Now, as far as the complexity concerned, the IP has enough complexity. Just to give you an example, in order to verify that the IP can compress n bytes of data correctly, there are 256 to the power of n possible combinations to verify. In addition, the IP must be compliant with industry standard software compressors, and as a data transformer, it must be able to handle an exponentially large number of input combinations. To address these problems, we decided to use FPV methodology to accelerate the IP development lifecycle. However, based on our prior experience of developing this IP, we were certain that this will be not enough to meet the aggressive schedule of 3 quarters, and we will have to look for other techniques which can shorten the development cycle even further. So we started looking for an answer to the question, are there any other FPV techniques which can help shorten the IP development lifecycle even further? Well, we found the answer as yes. Formal elaboration, design exploration, and formal sequential equivalence are powerful FPV techniques which can efficiently reduce the development time. In the rest of the presentation, I will provide details about these techniques along with the results showing a clear impact of deploying these techniques. Let's discuss the first technique, formal elaboration. Formal tools have capability of synthesizing the design and provide various design information such as gate count, flop count, latch count, etc. during the elaboration of the design. In addition, the formal elaboration takes orders of magnitude less time than the standard synthesis tools. Now keep in mind that the gate count reported by formal tools does not represent the actual gate count after synthesis. Even though the gate count reported by formal tools does not represent the actual number after synthesis, it can still be used to do relative area estimates for early impact analysis. For an instance, during POC phase, area estimation is one of the key tasks. It is required to determine feasibility of the proposed architecture. And even though it is an estimation, it should not exceed 20% of the final implementation to avoid late RTL changes. Now, one can take advantage of the fast design elaboration offered by formal tools to compute area estimates as shown here and reduce the length of this task. For example, to estimate area of our next generation compression IP during its POC phase, we first calculated the formal area of our next generation compression IP using its POC design. Then we calculated the formal area of our previous generation compression IP using its tape-out quality design. After calculating these two numbers, we applied percentage-based approach as shown here and estimated relative area change for our next generation compression IP. Here, the formal area represents summation of formal gate count, latch count, and flop count reported by the formal tool during the design elaboration. Reiterating one more time, the formal gate count does not represent the actual number after the synthesis. Another application of formal elaboration can be maintaining RTL quality. Now, throughout the course of IP development, non-synthesizable constructs such as combination loops or unintentional latches can sneak into the RTL code. There can be a potential risk of schedule slip if these issues are identified late in the IP development cycle. However, one can use the design information from the formal elaboration, implement gatekeeper checks to catch such RTL code submissions, and maintain the high quality of the RTL. So now you would think that we can do the same with traditional synthesis tools, then why not use them? Well, of course, this can be done by traditional synthesis tools, but there are some challenges with them. Standard synthesis tools may need additional time for setup, or may not be even available during the POC phase. Also, these tools tend to have long run times. This can significantly increase the length of the POC phase and result in schedule slip. In addition to this, their long run time makes traditional synthesis tools less attractive and unrealistic for implementing gatekeeper checks to catch the RTL submission with non-synthesizable constructs. Next technique that I would like to discuss is design exploration. Design exploration is a technique that is used to examine different behavior of the design. It is also used to get a feel for how the design acts under various conditions. Its execution requires describing the expected design behavior via cover properties and then using formal tools to identify if these conditions can be reached. And if reached, then what are different stimuli required to reach these conditions? This technique can be used to identify design bugs before the first RTL handoff to the PSV team, also known as early design bugs. Now you might be wondering, what are these early design bugs and why is it important to identify them? Let me throw some light at it. Until the first RTL handoff to the PSV team, there is usually no testing is done on the design. Hence, these early design bugs stay undetected until the first RTL handoff. Now, majority of these bugs are trivial bugs. Example given, incorrect state assignment or incorrect signal transition. But they can have significant impact because due to their existence, basic tests may fail and both PSV and design team will have to spend their time in root cause of these failures. This will cause delay in stress testing and may result in schedule slip. Let's understand this with an example. The figure shows a finite state machine diagram of one of the design blocks. The code in text box shows RTL implementation of arcs exiting from state B. Now, there are two arcs to exit from state B. One is associated with event 3 and the other with event 6. If you notice, the RTL code is missing implementation of the arc associated with the event 6. In other words, it is missing the next state assignment for event 6. This has caused state G to be unreachable in the design. Now, depending on the complexity of conditions required to trigger event 6, this bug can stay undetected for a very long time. However, using the design exploration, a simple cover property describing that state G should be reached can uncover this bug in few minutes. Here are some more examples where design exploration can be useful in flushing out such bugs. Now, each one of the examples mentioned here had helped saving some amount of time, but the ones that had helped saving most of the times are incorrect signal sensitivity, where instead of behaving as a pulse, the signal was behaving as a constant high. Next is incorrect parameters for memory pointers, which resulted in out-of-index accesses during reading from or writing to the memory. The last one is missing assertion of valid signals, where assertion of valid signals was not correctly aligned with the payload for some of the key interfaces. Now, before we discuss the third FV technique, let's quickly go over RTL change and its verification. RTL changes are constantly happening due to lint, logic, power, or timing fixes. Each RTL change verification requires verification of the new logic and re-verification of the existing logic. In constraint-based random verification methodology, verification of the new logic is usually completed by developing and exercising directed tests. However, re-verification of the existing logic is usually a major overhead and may require weeks or months of random regressions depending on the RTL change. One can think of using LEC method to address this, but it may not be useful as LEC cannot compare non-state matching designs unless they are very trivial. As we saw in the previous slide, the task of re-verification of the existing logic can be too much time consuming in RTL change verification activity. If I represent this task in a block diagram, then it would look like what is shown in the figure. And the goal would be to feed original RTL and RTL with logic changes to a comparator that can identify if both RTLs are equivalent or not. Now, with this in mind, let's move on to the last FV technique, which is formal sequential equivalence. Formal sequential equivalence verifies identical output behavior between two blocks of RTL. It is important to note that the verification is carried out at every clock cycle and irrespective of the state matching. User does not have to develop additional assertions or checkers to complete this verification. It is faster and exhaustive compared to the constraint-based random verification methodology. Let's not worry about the formal constraints block over here for now, as I will cover that in next couple of slides. So with that, let's move on to the application of this technique. As you might have noticed, various capabilities of formal sequential equivalence that I had mentioned in previous slide are actually solution to the problems associated with re-verification of the existing logic task of RTL change verification activity. Thus, leveraging formal sequential equivalence can significantly accelerate RTL change verification activity. To visually realize, if I represent my re-verification of the existing logic block diagram in terms of formal sequential equivalence block diagram, then it will look like what is shown in the figure here, where block 1 represents original RTL, block 2 represents original RTL with logic changes, and formal sequential equivalence functions as the comparator that lets us know if both RTLs are equivalent or not. Now, if you recall, in formal sequential equivalence block diagram, I mentioned about formal constraints. So let's discuss about that briefly here. Formal constraints are used to mask or disable any logic of the design. These constraints are optional and their existence depends on the application. For example, formal constraints are required for logic changes due to functional bug fixes. In this case, they are required to disable newly added logic when proving that the new design is equivalent to the original design, or to restrict the formal tool from exercising scenarios that can trigger the failure condition to prove that the logic changes did not introduce any new side effects. Formal constraints are not required for logic changes due to lint cleanup or code refactoring. However, they may be required for logic changes related to timing and power optimization. With this, let's go through some real-world results. We deployed these techniques in our compression IP development lifecycle. Using design information from formal elaboration played a key role during POC and execution phase. For POC, we provided the backend team with reasonable area estimates without relying on availability of the standard synthesis tools. This shortened the POC phase by 4 weeks. Now, from an execution perspective, we enabled formal elaboration as a part of our gatekeeper check and caught submission of non-synthesizable RTL code multiple times. This maintained quality of the RTL. Leveraging design exploration resulted in identifying 31% of the overall bugs. More importantly, since these bugs were found before the first RTL handoff to the PSV team, it enabled PSV team to shift their activities to the corner case testing with the first RTL handoff itself. Utilizing formal sequential equivalence to verify various RTL changes reduced PSV efforts for RTL change verification tremendously. This gave the PSV team more time to complete their sign-off activities such as functional and code coverage analysis, test bench review, etc. By deploying these powerful FP techniques at various stages of IP development lifecycle, we were able to deliver tape-out quality RTL for our compression IP 12 weeks ahead of schedule. To summarize, I discussed various FP techniques beyond FPV and their applications. The FP techniques discussed are formal elaboration, design exploration, and formal sequential equivalence. Their applications are relative area estimates and quality checks, identification of early design bugs, and acceleration of RTL change verification. I also demonstrated the effectiveness of these techniques, which are savings of 4 weeks from the POC phase, identification and root cause of 31% of the total design bugs before the start of PSV activities, significantly accelerated RTL change verification, and combining all together, delivery of tape-out quality RTL 12 weeks ahead of schedule. With that, I would like to conclude the presentation. Thank you all for taking the time for participating in this presentation. We would like to address any questions that you might have.